What I'd like to do first is lead you to a solution or solutions of the wave equation without really breaking a sweat, just nice and easy. So let's start out kind of backwards. Let's start out by supposing that we have a solution to the wave equation. So suppose U solves the wave equation. Let's call the wave equation WE. For short, WE. So suppose U solves the wave equation. Now, what happens if I take U and I plug it into the transport equation? Let's plug it into UT plus CUX. What comes out? Well, I don't really know. U solves the wave equation, so we don't know if it solves the transport equation or not. So something comes out. Let's call it W. Now here's the thing which is very interesting. W actually solves the backwards transport equation. W solves WT minus CWX equals 0. And this is true by virtue of the fact that U is a solution to the wave equation. Well, let's prove it, because that's the best way to really understand what's going on here. So, proof. Now the proof is not difficult, it's a computation, but we have to be careful and make sure that we understand what we're doing every step of the way. So let's begin with this equation, WT minus CWX equals 0. And let's plug in the definition of W, and that's UT plus CUX. So we start off with WT minus CWX. Okay, this is equal to, plugging in the definition of W, UT plus CUX t derivative minus CUT plus CUX x derivative. Okay, well, let's take all these derivatives inside the parentheses. So I have a t derivative of UT, and that gives me UTT, plus a t derivative of CUX, and that gives me CUXT. Now minus C times an x derivative of UT, so that gives me minus CUTX. Now I have minus C times C and an x derivative of UX, so I have minus C squared UXX. Now, what does this equal? Well, UTT minus C squared UXX, that's 0, because I know that U solves the wave equation. So let's write that down. The outer terms here, this guy and this guy, combine to be 0, and that is because U solves the wave equation. Now, on the other hand, these two interior terms right here, UXT and UTX, these things also combine to 0. And why is that? Well, whenever U is a sufficiently nice function, the partial derivatives of U commute. So UXT is equal to UTX. This is sometimes called Clairaut's theorem in your multivariable calc class, where you learn about partial derivatives. And this fact really has nothing to do with the wave equation at all. It's interesting to note that what we've shown with this proof is something that's a little more general than what we set out to show. We set out to show that if U is a solution to the wave equation, and we define W as UT plus CUX, then W satisfies WT minus CWX equals 0. What we've actually shown with this proof is that the two equations are equivalent. So in other words, if we define two functions U and W by these two differential equations, then U must be a solution to the wave equation. And the easiest way to see that is really just to erase the two terms that we know are always 0, independent of the wave equation. And we see that if UT plus CUX equals W, then WT minus CWX is the wave equation in U. So the only way that WT minus CWX is 0 is if the wave equation is satisfied by U. So let's rewrite things. Let's erase all this suppose business. And let's say that these two equations are equivalent. utt minus c squared uxx equals 0 if and only if these two equations are satisfied. So there are equivalent sets of equations. While we're at it, we might as well just get rid of this junk down here just to clean it all up. So we see that really all this proof consists of is computing wt minus cwx and seeing that it's equal to the wave equation in u, and therefore one is 0 if and only if the other one is 0. I promised that this would be a no-sweat way to find some solutions to the wave equation, and in fact it's more than that. But let's look at how we can generate some solutions to the wave equation using this observation here. So if we can find a w that satisfies this transport equation, which we can do, we know how to solve the transport equation in general, then we can take that w, plug it in right here, and again solve another transport equation with something on the right hand side to get a solution to the wave equation. So for example, if I was to take w equals 0, take w equals 0, that's a perfectly good solution to wt minus cwx is 0. Plug in that w on the right hand side here and solve ut plus cux equals 0. And I can do that. We know that the solution to ut plus cux equals 0 is u of xt equals p of x minus ct, where p is any sufficiently nice function. That will provide a solution in turn to the wave equation. Now you may have noticed that when I started this argument, I sort of arbitrarily took u and plugged it into ut plus cux and called the result w. And as a result, I got these two equations, two transport equations, as being equivalent to the wave equation. On the other hand, I could have just the same taken u and plugged it into ut minus cux and then called the result v. Then, by a similar computation, I would have noticed that vt plus cvx is in fact equal to 0. And so these two transport equations are also equivalent to the wave equation. What does this mean? Well, it means that I can redo this example just the same. I could take v equals 0. That's a perfectly good solution to this guy. Not the only one. I'm just doing an easy one, for example. I could take v equals 0. Then I would have to solve ut minus cux equals v, which is 0. And I know a solution to that would be any function u of xt of the form q of x plus ct, where q is a sufficiently nice function. I think I can say safely that without too much work, without really breaking a sweat, we've got a lot of solutions to the wave equation. We've found that any solution to the forwards transport equation, p of x minus ct, is a solution to the wave equation, and any solution to the backwards transport equation, q of x plus ct, is a solution to the wave equation. Now, you may or may not know this at this point. We haven't really discussed this yet. But the wave equation is what's called a linear partial differential equation. That means the same thing that it does in ordinary differential equations. It means that if I have two solutions to the equation and I add them together, I get another solution to the equation. So I can add together these solutions that I found by slightly different methods. I can add p of x minus ct and q of x plus ct for whatever p and q I want to choose, and I get another solution to the wave equation. If you're familiar at all with the wave equation, then you've probably seen this formula before. This formula is sometimes called D'Alembert's formula, and it is a general solution to the wave equation. that means that any solution at all to the wave equation has this form. This is not just a particular collection of solutions. Any and all solutions have this form. Now, the argument that we've given here doesn't prove that. It doesn't prove that every solution has this form. It only allowed us to arrive at this formula and say, okay, this formula gives us lots of solutions to the wave equation. We'll prove that this is in fact the general solution in a moment. But before I do that, let me give you a little puzzle. And this puzzle will be just a verification that really this is the case. Now I want you to check that the function u of xt equals cosine of t times sine of x solves the wave equation utt equals uxx. So in other words, with c equals 1. Now the question is this u of the form p of x minus t, again c is 1, plus q of x plus t. So what I'm asking is, can you find functions p and q such that the function cosine t times sine x, which is a solution to this wave equation, is a sum of a wave moving to the right and a wave moving to the left? Go ahead and pause the video and give this puzzle some thought. In the next slide, we're going to prove, in fact, that any solution to the wave equation has this form. So your efforts will not be fruitless, I promise. Okay, it's time to show that the formula we obtained on the last slide is, in fact, the general solution of the wave equation. Now, I put general in quotations here because we haven't discussed a few important things related to solving the wave equation. We haven't talked about boundary conditions. We haven't talked about initial conditions, and we also haven't mentioned the domain of definition of the equation. So we'll ignore all that for now. These things are important, but they're not essential to this discussion that we're having now. All right, then let's begin our proof. Remember in the last slide that we discovered the wave equation is equivalent separately to two sets of transport equations. The first one being ut plus cux equals w, and then wt minus cwx is 0. And the second one being a little switch of signs, ut minus cux equals v, and then vt plus cvx is 0. Well, if you've watched my previous videos, then you're hopefully an expert on the transport equation. So you know that we can actually solve both of these transport equations, the one in w and the one in v. The solution, the general solution to the w equation will be w of xt is equal to f of x plus ct, where f is some arbitrary function, and the general solution to the v equation will be v of xt is equal to g of x minus ct, where g is also some arbitrary function. We can take this f and plug it in for w, and we can take this g and plug it in for v, and we get the following equations. ut plus cux equals f of x plus ct, and ut minus cux equals g of x minus ct. These are two transport equations involving some known functions f and g. Our job now is to find u from these two equations. Now, in my opinion, the easiest way to do this is to use a little trick. We first add the two equations together, and then we subtract them, and we compare the two results. So let's do that. The sum of the left-hand sides of the equations will be ut plus cux plus ut minus cux. So that gives us twice ut is equal to simply f of x plus ct plus g of x minus ct. And the difference of the left-hand sides will be ut plus cux minus ut plus cux. So I'll get 2c ux equals the difference of the right-hand sides. It's f of x plus ct minus g of x minus ct. Now, we can clean it up just a tiny bit if we move the 2 and the 2c over to the right-hand side. So I'll put this as a 1/2 there, and a 1/2 there, and a 1 over 2c here, and a 1 over 2c here. Notice now that I have ut and ux given in terms of f and g. So in order to find u, I really just need to carry out an integration in either one of these or in both and compare. Let's do that now. It's actually not too hard to integrate these guys. For instance, integrating the ut term, I would need to take an antiderivative of this right-hand side with respect to t, and that would involve having some antiderivatives of f and g and putting some constants out in front to cancel the c and the minus c when they come out by the chain rule. So let's do that. We need antiderivatives of f and g, so let's choose a capital F such that capital F prime is equal to little f, and a capital G such that capital G prime is equal to little g. Then it's not hard to check that the ut integration would give me a function u of xt, which is 1 over 2c, capital F of x plus ct, minus 1 over 2c, capital G of x minus ct. Similarly, when I carry out the ux integration, I'm going to get a function u of xt, which looks like, well, there's no c in front of the x here, so I don't need to bring the constant out to compensate, but I already have a 1 over 2c here, and so I'll get 1 over 2c capital F of x plus ct minus 1 over 2c capital G of x minus ct. And this is great. I mean, we want the u's to be the same. But hold on one second. And if you're watching carefully, you would object and you'd say, when I carry out a t integration, I actually add, in addition, a function of x, which is an arbitrary function. And the reason is because that t partial derivative will kill off any function of x. And when I carry out that x integration, I add an arbitrary function of t, because the x partial derivative will kill off any arbitrary function of t. Now I claim we don't need to worry about these functions. The reason is we are comparing two u's which need to be the same. These expressions involving capital F and capital G are the same. And so these functions of x and of t must also be the same. Now the only time two functions are the same when they're functions of different variables is if they're both constants. So let's cross them out and replace them with the addition of some constant k. Now I don't really care about adding in some constant. And the reason is because f and g are arbitrary functions, and so I could easily absorb that constant into one of these arbitrary functions without changing my argument at all. So let's cross off these constants too, and let's get to our conclusion. So what is the conclusion? Well, we showed that solving the wave equation is the same as solving either of these sets of transport equations, and we have solved those transport equations. So we found a general solution to the wave equation, and it looks like u of xt equals 1 over 2c, capital F of x plus ct, plus minus 1 over 2c, capital G of x minus ct. Now, capital F and capital G came from arbitrary functions little f, little g. They were their antiderivatives. And that means that capital F and capital G are perfectly arbitrary. And since capital F, capital G are perfectly arbitrary, so are 1 over 2c times f and minus 1 over 2c times g. So we might as well just call these things new arbitrary functions, p of, not p, but q of x plus ct, because this is the function of x plus ct, and call this guy p of x minus ct. So if we simply rename our little function 1 over 2cf and minus 1 over 2cg, then we get our general solution to the wave equation in the form that we originally wrote it.